Should we start?
That's good with me.
Okay. Good morning, everyone. Thank you for being here today in another session of the Inria Academy. In our third masterclass, I want to welcome the 300 participants today from Chile, Mexico, Brazil, United Kingdom, Germany, and France. I remind you that this masterclass will be simultaneously translated into Spanish, so you can choose the language in the bottom of the tool. And the chat, as you may have seen, will be open for questions and for a better interaction, okay, with Gaël. It is for us a great pleasure to have here with us Gaël Varoquaux. Gaël is a researcher at the Pca Inria team, with important research results in the areas of neuroscience, cognition, and brain imaging. Just because of that, it would be awesome to have Gaël invited to this Inria talk. However, Gaël has done more than that. He's one of the main responsibles for Scikit-Learn, one of the main machine learning frameworks, and a big pride for Inria. He's currently director of the Scikit-Learn operations at Inria Foundation. Scikit-Learn is the result of many years of work and personal commitment of Gaël and the rest of the collaborators, and also the machine learning community. It is a truly open source software, and that is one of the main reasons behind the growth and democratization of the use of machine learning. It is extensible, efficient, and without an agenda imposed by one company interest. Because of this high impact work, Gaël and collaborators have received an important award by the French National Academy of Science last year. However, I think they all receive a daily award when more than 1 million researchers around the world write, import, Scikit-Learn, and start using machine learning. Thank you, Gaël, for accepting being here with us today. I will give you the floor and enjoy the masterclass.
Thank you very much, Nayat, and thanks to everybody for joining us. I think if it's fine with everybody, I will start because there's a lot to cover and we only have an hour and a half. So if I'm speaking too fast, Amanda, don't hesitate to slow me down. So I will share my screen. Yep, that's the correct screen, and we will move to the materials. So as materials today, I will use the SciPy lectures. You can find them online. They're at scipylectures.org. And I will use the chapter on Scikit-Learn. Surprise. So if you want to follow, you can go to scipy-lectures.org and click on the chapter for machine learning. So my goal is to give you in the time that I can cover an introduction to Scikit-Learn and to a few of the concepts that are behind Scikit-Learn and basically statistical machine learning. I'm not sure exactly how far I will be able to go. I was asked to do something that covers as much as possible. So I realized that things might be a bit fast. You have the materials, they're online. And I think the ideal way to learn more is to play with them a bit more. I won't be fully running them because it takes longer, but if there are any questions, I'm happy to take them and I can demo things as we go. I'm also monitoring the chat on the side, so do not hesitate to ask questions. So I'll start by defining a bit the problem settings and the basic principles of machine learning with Scikit-Learn. Then I'll go a bit more into supervised learning, and I'll give a few examples. Then I'll cover how do we measure prediction performance. I'll discuss a bit unsupervised learning. I'll try to introduce the very important concept of the pipeline. And if we have time, which is uncertain, I might cover the problems of parameter selection and related validation and testing. So, what is machine learning? Machine learning is really about building something that you can either see as a tunable program or a very flexible statistical model that is able to predict from data and to apply to unseen data. So the idea being that I'm going to use labeled samples, so data with labels, to learn a link between this data, these measurements, and those labels. So for instance, I might have two labels, two measurements that you can see here, and I might want to separate the light blue from the dark brown dots, in which case I need to learn that I need to draw a separating line between the two. So this is a fairly simple example. It's an example of a classification task. I'm trying to separate two classes. I might want to predict a continuous variable. If I'm trying to predict a continuous variable, then I call this a regression task. And it's, some elaborate form of curve fitting. In Scikit-Learn, all our data is represented as a NumPy array. So a NumPy array is a table of numbers. And here we are focusing on measurements that are represented with a 2D array. So an array that has n features, number of columns, and s samples, number of rows. So it means that we're going to have to describe all our data as rows with a given number of numerical features. And of course, this is part of the work, and I'll come back to this. So one way to illustrate this is to consider a historical example, which is that of classifying irises. Irises are flowers, and there are different kinds of irises. And the question that a researcher was historically interested in was, can we derive simple rules that allow us to distinguish between those types of irises? So I want to design an algorithm that will recognize iris species. And so I've got those irises, and I'm going to need to build a data matrix that I can feed in Scikit-Learn. And Scikit-Learn is stupid. It can only take a 2D array of size n samples times n features. So in such an example, what would n samples refer to? It would be the number of irises that I have. And what would n features refer to? Well, that's more of an open question. I need to go from this problem of irises to a set of measurements that I can feed in my algorithm. And so the historical way this was approached is by measuring the characteristics of the irises and measuring what's known as their sample. So the historical researcher went out in the field and measured the length of the sepal, which is here, and the petal, which is inside. And he built a table with different irises of different species, with each time the length and the width of their sepal and their petal. So what you can see is that he transformed the original problem, which is a problem of the flowers, into a problem of numerical measurements by using the width and the length of the petal and the sepal. Now, once we have this, we have 4 features: sepal, length and width, petal, length and width. And we have 3 types of irises that we need to predict, which are the kind of irises, and their names are Setosa, versicolor, and virginica. I don't know how this translates to Spanish. So this data comes in with Scikit-Learn. It's a historical example. So we can load it with Scikit-Learn with the following lines in Python. And then we have this iris variable, and we can look at the corresponding data, and we can look at its shape. And so we print iris.data.shape, and the result is 150 times 4. So what's 150? 150 is the number of irises I have in my data set. So it's the number of samples. And 4 is the number of feature per iris. And here it's 4 because it's sepal and petal times length and width. Okay? So I can look at my first iris, and my first iris is described by 4 numerical features, which are those numbers. I can look at the associated target. So for each of those measurements, I have a target, which is the number of the class that I'm going to try to predict. So you can see here that in my data set, I have class 0 first, then class 1, then class 2. And so my problem is now going to go from this type of measurement to this type of measurement. So I can try to visualize this data. Now, I can visualize, for instance, the sample width and the sample length and use the color to denote the class. So I've done this here. So I'm looking at only 2 of the features because I can't do 4D data visualization. But even looking at 2 of the features, I can guess that I can find separations, for instance, with a line along here, okay? So by looking at this, I can start to understand the problem of machine learning, which is to find numerical rules on these data to learn to discriminate those classes. And now we're going to look at doing this with Scikit-Learn. And before we apply Scikit-Learn to data, I want to introduce the core principles of the API of Scikit-Learn. And I'll do this with an example using the linear regression. So I can import the linear regression object. I will import it from linear model. Then I can instantiate a model. So I will instantiate linear regression, and I can give parameters to this model. Those parameters are then found as attributes of the model. And if I print the model, I will see the parameters. Now I can fit it on data. So I will create X and Y, and linear regression is for the Y that takes a continuous value. So I will create one matrix with X and one matrix with Y. There's one detail, which is that Scikit-Learn wants input matrices that are 2D. It needs to be 3 samples times 1 feature. So I need to add an axis. This is a standard NumPy syntax to add an axis. And now capital X is a 2D matrix that is 3 samples times 1 feature. And once I have this, I have X and Y. I can fit the model on this. So for this, I need to call model.fit. And it returns a fitted model. So now that I have a fitted model, I can look, if I want, at the estimated parameters. And these are found in model attributes that finish with an underscore. So coef underscore is the coefficient of the fitted model. And now that I have this model, I can do prediction, I can do supervised learning. So in supervised learning, in general, we have a data set that consists of both features X and labels Y. And we are constructing an estimator that will predict the label Y of an object given the set of features. And as I've mentioned before, we have two general settings, those of classification and those of regression. Classification being when the output is a discrete variable, like in the iris setting. So to give you an example of classification on the iris data set, I can use the nearest neighbor classifier. So for this, I will import the nearest neighbor classifier from Scikit-Learn.neighbors. I will also load my iris data set. Then I will create my nearest neighbor classifier and I will tell it to use a single neighbor. So that's a parameter of my classifier. Then I can apply it on the data and the labels. And once I've done, KNN is now classifier and it can predict. And for this, I can use the predict method. So I go knn.predict. And for prediction, I also need to give a 2D matrix. And this time I will give a 2D matrix with only one sample, only one row. And I will ask my KNN classifier what kind of iris has 3 times 5 centimeters sepal and 4 times 2 petal. Okay, so this is how I use Scikit-Learn. And so this is the kind of prediction that I've learned. You can see it here. I've fitted my KNN classifier on the dots, and I've asked it to predict on the rest of the data. Okay? So this is for classification, and for regression, we can do this with the linear regression object. And here I will create a bit of random data where Y is related to X with a bit of noise. And then I will instantiate my linear regression. I will fit it on the data, and I can predict on new data points. And I will take those new data points to be regularly spaced between 0 and 30 with 100 data points. Okay, so this is what I get. My blue dots are the data that I used to fit the model, and my line is the prediction of the model. It's a line because the linear regression is a linear model. Okay, so really the API of Scikit-Learn is quite easy. I need to instantiate the model, I need to fit it, and I need to predict. This is almost all you need to know. I think we can stop here. Well, maybe not. We can look at a bit more details. So all estimators have fit. Some estimators have predict, and these are the estimators for which we do supervised learning. I will later explain the estimators that do unsupervised learning. Some estimators have predict proba for classification settings. So for these settings, the estimators are able to return the probability of a class. So if I have two classes, predict proba will return two values, the probability of the first class and the probability of the second class. Some estimators have a score method, which gives me the goodness of fit of the estimator, so the error on data. And the error, the convention is bigger is better. In unsupervised setting, the estimators can transform the data. And I will cover this later. I now want to talk a bit about regularization to explain what it is and why it is necessary. In general, it's useful to prefer simpler model. And let me give you an example. Suppose you are using a one nearest neighbor estimator. So an estimator that given a new data point will look at the closest data point it has already seen and attribute the corresponding label as a prediction. If we have such an estimator, how many errors do you expect on your train set? The answer is none, no errors. And the reason is that the estimator will look, if you give it a data point, it will look at its closest data point. The closest data point will be the same data point because this data point is in the train set. And as a consequence, it won't get it wrong. So this tells us the first thing is that the error on the train set is not a good measurement of prediction performance because it's easy to predict things I have already seen. It's much harder to predict things I have not seen. Also, in general, we will learn that we need to accept error on the train set. And so for this, we're going to use regularization, which is that we're going to force models to be simpler for a certain definition of simpler, even if this leads to more errors on the train set. To give you an example, here is data that is generated with a ninth order polynomial and some noise. And now I will fit on this data. So the data is here. And now I will fit on this data a fourth order and a ninth order polynomial. Okay? So the fourth order is the blue line, and the ninth order is the orange line. So with your naked eyes, which model do you prefer? The fourth order one or the ninth order one? So typically people prefer the fourth order one. And the reason is our intuition is it's less noisy. And this is interesting because we're forcing a model that is simpler than the ninth order because it gives us less noisy estimates. Now, if we look at the ground truth, the model that we use to generate this data, it is somewhat in between. So the idea of regularization is that we will prefer models that are simpler to avoid capturing noise. And it's something that is present everywhere in machine learning, and most scikit-learn estimators have a parameter to tune the amount of regularization. With the k nearest neighbor, the parameter is k, the number of nearest neighbors. If we put k equals 1, we have no regularization. We're getting no errors on the training set. But if we use large k's, we will average many neighbors to make a decision. And as a consequence, we will remove noise and have smoother decision boundaries in the feature space. Another example is that of controlling the complexity of the decision boundary. We can use a linear model. A linear model is the simplest possible model. We can use a nonlinear separation. It will capture more complex shapes, but it can also more easily capture noise. Now I will illustrate those concepts on a simple but real problem, which is that of classifying handwritten digits. And for this, we can load the data in Scikit-Learn using sklearn.datasets.loadDigits. And so when we call this function, we will get the digits object. And what this data really is a set of many images of handwritten digits. And the task is to recognize the handwritten digit. So it's to predict whether the digit is 0, 1, 2, 3, etc. So is this a regression task or a classification task? Well, even though the output is numbers, this is a classification task, because what matters is that I predict the correct digit and not that I predict close to the correct digit. So we have those pictures and we need to fit a classifier to them. So to do this, I am given images, digit.images, which are of dimension 64. They are dimension 8 by 8. And I can look at them, but I will need to feed them into the classifier. To look at them, unfortunately, I cannot visualize data points in a 64 dimension. So I can reduce the data using a principal component analysis. And for this, I will use another type of scikit-learn object, which is the principal component analysis. This object can transform the data by projecting it in a lower dimension. So I will take the 64 dimension data, and I will project it in 2 dimensions. And I can do this by creating the Pca object and then calling fit transform on it. And if I do this, I go from data that is of dimension 64 to data that is of dimension 2. And now that the data is of dimension 2, I can visualize it. So this is what I get. I get a cloud of points in dimension 2, and I have given a different color for each point. And what you can see here is that the points separate themselves. So given this representation, which number do you think the classifier might have trouble distinguishing? Basically, this question amounts to, where do I have a lot of overlap in those numbers? You can see that it's around here, for instance. So 1 seems to be hard to distinguish from 8, from 5. This is probably because some 8s are written in a very narrow way and some 5s are written in a very narrow way. However, it is important to keep in mind that the data is not only in those 2 dimensions that we're looking at, but is in a higher dimension. And we're going to give this complete dimension to the classifier. So the classifier may be able to find separations that we cannot see. So now that I've looked at this data, I will use simple models to try to build classification. And maybe the most simple classification model, classifier that I can use is the Gaussian naive Bayes. In Scikit-Learn, we can find it under scikit-learn.naivebayes.gaussian_nb. Okay? So what I will do is that I will import this model from Scikit-Learn, and then I will split my data into a trained set and a test set. And the reason that I do this is because, as I mentioned before, I cannot judge the quality of prediction on data that I have used to train the model. So I have a question, which is, how does the democratization and the reproducibility of machine learning are combined? Democratization of machine learning, to me, is about putting machine learning in the hands of everybody. Reproducibility means that the outcomes, whether they're a model that predicts or a finding on the model that predicts, are trustworthy. And the question is, how important are these? And in my opinion, they are very important, because machine learning has a huge potential. Machine learning can change many things in people's life. And so we need to make it easier for people to understand machine learning and to build things themselves with machine learning. And this is one of the goals of Scikit-Learn, is to make it easy for people to build things themselves. And this is maybe what I'm trying to illustrate today. So to go back to my example, we're trying to build a classifier that separates digits And for this, we're using the simplest possible classifier, which is the Gaussian naive Bayes. And we're splitting the data in train and test set. And for this, we're going to use the train test split to separate X train, X test, Y train, and Y test. And now we can fit the model. So we're going to create the Gaussian naive Bayes object, and we're going to fit it on the data. So X train and Y train, and we can predict on left out data. And then we can compare our prediction to the expected labels, and we can quantify the error. Okay, so here I am plotting the data and the predicted label, and I'm using different colors. Green means the prediction was correct. Red means the prediction was incorrect. So here you see an example of incorrect prediction, where if I look at the data, it looks like a 9, but the classifier predicted an 8. Okay? So it's important to keep in mind that we need to split the data in train and validation sets, train and test set, to be able to properly measure our prediction accuracy by looking at the difference between the predicted labels and the actual labels. So I have a question on the Pca step above. And the question is, we've reduced the data to go from 64 dimensions to 2 dimensions. How do we know that the 2 chosen dimensions are the most representative of the problem? Well, the Pca knows nothing about Y. It's called an unsupervised learning method. So it can't do an informed choice with regards to Y. So what it does is it takes the axis of the data that capture the most variance. This is the criterion of the Pca. It tries to capture the most variance. However, variance may not be the most useful information. So Pca does not give us any other guarantees than capturing variance. It is still quite useful in general. So I've shown you how we can apply a very simple model to data to get a prediction. One thing that I forgot to tell you is that although those are images and they're 2D, each sample in Scikit-Learn is 1D. So we have flattened those images. This is how we get 64 dimensions. So now that we have such a prediction, we can measure the performance quantitatively. We can do this in a naive way by simply counting the number of times we got it wrong. And here we see that this naive Bayes classifier got a correct answer more than 80% of the time. So there are other ways of measuring the error, and in general, in Scikit-Learn, they're found in this Learn.metrics submodule. And one very useful metric is the classification report, which combines several measures to print a table with the result. So if I take my expected labels and my predicted labels, I can print the corresponding classification report. And what I get is, for each class, I get a measure of precision. So what fraction of the detections in this class were correct detections? The recall, what fraction of this class did the classifier get right? So for the class 0, all the predicted zeros were actual zeros because I have a precision of 1. However, the classifier found only 91% of the zeros. The F1 score is a combination of those two metrics, and the higher it is, the better. And the support is the number of zeros that were in the test set. So this gives me a complete view of the error per class. And here I have 10 classes. I can also look at the confusion matrix. So I can print it using metrics.confusionmatrix. And this tells me what 0, so the first class is 0, to which class it is confused. So 0 is confused to 1, 2, 3, 4. 0, the classifier mistakes some zeros to 4s, some zeros to 5, 6, 7, etc. And in particular, we can see that number 1, which is here, is often being labeled number 8, which is here. Okay, which corresponds with the intuitions that we had developed earlier, looking at the two-dimensional embedding. So this was an example of a classification task. I want to stress that we used an extremely simple model, the naive Bayes, and it's really the simplest model. We can use more elaborate models, and I will detail them a bit. I have a question that is asking me what makes the naive Bayes naive. So it's called a naive Bayes because it models each features independently. It doesn't capture well the relationship between features. In general, this is a limitation. However, it enables it to be very fast, and also it is a regularization, so it is a very simple model that is less likely to overfit. I will cover later how we can compare different models to be able to choose the best one. And I will now discuss a new example, one of regression. And I will use this to introduce a different model. So one thing that you can see is that there are many different models in Scikit-Learn, and it's useful to know quite a few of these because they all have strengths and weaknesses and can be useful in different settings. So here we will look at a data set on the prices of houses that is available in Scikit-Learn. And actually, we are removing it from Scikit-Learn, so I will need to update this course. So, this data set has over 500 data points and 13 attributes. So, let us look at those different attributes. We can print the description of the data set. So when we print the description, it tells us information in the different attributes, such as the crime rate of the region where the house is, the proportion of the residential land in the region where the house is, the proportion of businesses where the house is, the number of rooms of the house. And now the challenge is going to be to relate all those features to the price of the house. And the price of the house is stored in the target variable. And here I am looking at the histogram of the target variable. And one thing really stands out, to me at least, on this histogram. And it's the fact that we have a nice price distribution and then it goes up here. And the problem here is that the data is truncated. Any house that was more than $50,000 has been collapsed to $50,000. So this is a bias of the data. And it shows us that it's very important to look at our data to understand its biases. Now, in terms of looking at the data, what I can do is that I can plot the joint distribution of the target that we're trying to predict with each of the features. So this is the price as a function of the crime rate. And you can see that if the crime rate is smaller, the price tends to be higher. I can look at the price as a function of the number of rooms, and you can see that if the number of rooms is larger, the price tends to be larger, which makes sense. So, looking at these distributions, you can see a challenge of this data set, which is that many of the different features have different distributions. There are features of different nature. Here I have a binary variable that tells me whether the house is next to the river or not. The river is called the Chase River. So I need to combine information of very different nature. And this is often the case in data sets that come from sociodemographic databases, for instances. And for this, I will use a specific, I'm going to skip all this. Well, so I can fit the, I can use a linear regression for this. And if I use a linear regression, so I can fit it on the data and I can predict. And this is a plot of the predicted price as a function of the true price. And what you can see is that for the true price, we're undershooting. We are under predicting the true price. And one of the reasons is that this data set is not really linear. And moreover, the notion of linearity on this kind of data is difficult because I, I can't easily build a linear model on features of different nature. It's possible, but it's difficult. So what we can do is that we can use a gradient boosted tree regressor. So a gradient boosted tree regressor is a regressor that is very well suited to data of very different nature. In particular, this kind of data on sociodemographic databases. So a mixture of discrete entities and continuous variables. So gradient boosted trees are very well suited for this, and they are used a lot in the industry for this reason. So they are found in Scikit-Learn.ensemble, and I can import Scikit-Learn.ensemble.gradient boosting regressor. Okay, and if I do this, I can just replace linear regression in this code, and I can use the gradient boosted regressor. And this shows you one of the strengths of Scikit-Learn is that I need to change very little things to be able to swap one model with another one. So in general, if you have data that comes from databases with features of different nature, I would advise to look at gradient boosting, and I would advise to look at the gradient boosting regressor if it's a regression problem, the gradient boosting classifier if it's a classification problem. And we have a new version of these that is faster, that is called the HIST gradient boosting regressor. Let me type this for you because this is very useful. So in the recent versions of Scikit-Learn, we have the HIST gradient boosting classifier and HIST gradient boosting okay, so I typed this wrong. Well, when I have a problem like this, what can I do? I can Google. And oh yes, thank you, Olivier. Thank you, Loic. Loic is reminding me that I need to import Scikit-Learn.experimental. Yes, I need well, I need to do this as it explained here. Okay. And now I can import. So as you can see, this is still experimental, but it's going to come out of experimental in the next release. And this is the model that is probably the most useful if your data is made of databases with columns of different nature, which in certain applications is very common. All right. So now that I have this, the question is this useful both for classification and regression? The answer is yes. The HIST gradient. So I have two variants of the HIST gradient boosting. I have the HIST gradient boosting classifier and the HIST gradient boosting regressor. And both are very useful It's really the nature of the data. If your data is databases, they're very useful. In general, I would probably say that those models are the most useful models of Scikit-Learn these days. If you have reasonably large data, so in the thousands of samples, you can probably try to use them by default. So, as you can see, one of the difficulties of Scikit-Learn and machine learning is to know which model to use, because how to use a model is in general quite simple. I just need to fit it and then I can predict. This comes a bit with experience and a bit with knowing simple rules, such as to experiment with the gradient boosting regressors. But also, a lot of this is by comparing models empirically on the data. And I will discuss a bit how we can compare those models. So I can create a k-nearest neighbor regressor. I can fit it to data, and I can measure its confusion matrix. Okay? I can do the same thing with other models. And what I will need to do is that I will need to measure their performance on test set to make sure that I have a good measure of performance. For this, I can use the validation set, so I can use the train test split to leave out data, and then I can get a correct measure of performance for my two models. And I can compare the two models. And then I can select the model that works best. So I can select the model that gives the smallest error on the validation set. For instance, here I am comparing three kinds of models: the Gaussian naive Bayes, the k-nearest neighbor classifier, and the linear SVC. And I will measure their error on the test set. So each time I will fit the train set and measure their error on the test set. And then I can choose the one that predicts best. So here, it's the k-nearest neighbor classifier. I can also compare different parameters of the model. So here I'm looking at a variety of parameters, the number of nearest neighbors, or the loss in the linear SVN. And this is how I can empirically choose my best model. Here, in the first example, I've done this using one single test set. However, I may want to do this many times, splitting many times, because I will get a better measure of my prediction performance. And you need to keep in mind that those measures are noisy measures. They're imperfect. And if I want to choose the best model, I need to work to get the best measure possible. For this, I can use cross-validation. The idea of cross-validation is to repeatedly split the data in train and test many, many times. And Scikit-Learn has tools to implement this cross-validation. There is, for instance, cross-val score, which is found in Scikit-Learn.model selection. And the way it works is that I give it a model X, Y, and optionally the number of splits that it needs to do or how it needs to do those splits. So here I'm asking it to do 5 splits. And each time it will split out data, train on the train set, test on the test set. And now we get 5 measures of error. And we can compare those measures of error across the different models to pick the best model. So we can use different splitting strategies, and this is done by passing objects into the CV arguments. So for instance, we can do a shuffle split. The shuffle split will shuffle the data and then split it. The nice thing with the shuffle split is that I can increase the number of splits, keeping the same fraction of the data in the test set. So I can compute many splits and average across those many splits. There are many different cross-validation strategies, and they are detailed in Scikit-Learn, in the Scikit-Learn documentation. Now that I have this technique to measure the performance of a model, I can use it to tune its parameters. So for instance, the nearest neighbor classifier has the parameter k, and I may want to tune the parameter to take the best possible model. This is known as hyperparameter optimization. Another example is that of ridge regression or lasso regression, which are both linear models that have a parameter, which is a regularization parameter. And I need to set this parameter empirically. So I can compare those two models, the ridge and the lasso. The ridge and the lasso are two linear models, but they have a different regularization. The regularization of the ridge forces the model to keep small coefficients. The regularization of the lasso makes the coefficient sparse, which means it gives a small number of non-zero coefficients. So I can compare the ridge and the lasso. So for this, I will use cross-val score on ridge and lasso. And I'm computing the mean of cross-val score, and I get two different answers. The ridge, I get 0.4, and the lasso, I get 0.35. So in general, in Scikit-Learn, bigger is better. So given this experiment, I will conclude that the ridge is a better model for my data. However, both ridge and lasso have a hyperparameter known as alpha, which tunes the amount of bias that we put in the model. And we need to put just the right amount of bias. If we put too much bias, we will have a model that is too simple and it won't predict well. If we put not enough bias, we will have a model that is too noisy. And here, I haven't done this. So what I can do is that I can vary this parameter value, alpha, and I can use cross-val score each time to compute the prediction accuracy for the different values of alpha. So I've done that here, and as I vary alpha, you can see that the models have an optimal, and then they predict less well. So I have two different optimals for Lasso and for Ridge. So based on this figure, which model should I prefer? The Lasso or the Ridge? Well, based on this figure, it seems that the Lasso predicts better. So I would conclude that I should prefer Lasso. However, can we trust those results? Here, I have used the data to select the best alpha parameter. Given that I've used the data to select the best parameter, I need another test set to evaluate my model, because I can never evaluate a model using data that I have already seen. And so for this, we need a way of selecting alpha only on the trained set, never looking at the test set. And the way we will do this is using grid search CV, which is an object that will take a model and take a list of parameters to vary, well, a dictionary of parameters to vary. It will perform internal cross-validation. So grid search CV, when I fit it inside grid search CV, it will by itself do cross-validation and select the best parameter. And it will return a model that is fitted with this best parameter. Okay, so if we run it, we see that it selects for Ridge a best parameter of 0.06. So here it makes it. And for Lasso, a best parameter of 0.01 here. So I'm going to skip this. Well, the only thing you need to know here is that Ridge CV and Lasso CV do the same thing as grid search CV, but they're specific to Ridge and Lasso. And now I can do a proper cross-validation. So now what I'm doing here is I'm doing a cross-validation on a model that is itself using internal cross-validation to select alpha. So each of these models is not given a single alpha, it's given a list of alpha. And internally, what it will do is it will do cross-validation to select the best alpha, okay? So it means I'm doing cross-validation on models that themselves select the best alpha. And if I do this, well, I don't know why you can't see it here, but if I do this, I will find that actually Lasso doesn't perform as well as Ridge. And the reason is that if we go back to this curve, the peak here is very narrow. And so it's very hard to select the best possible parameter. So if I select the best possible parameter for one data set, and you give me a new data set, I will fall off. And this will cost me a lot. So the Ridge doesn't have this problem. It's much more flat. And selecting the best parameter here was an overfit. I had learned something that does not carry out to new data. So I have another 15 minutes left, and I would like to talk about chains of transformations. And I will, for this, I need to talk a bit more about unsupervised learning. So as we've seen before, unsupervised learning, such as Pca, can be used to transform the data. We've seen this before. We can reduce the data set to lower dimensions using Pca. For this, I need to call the Pca.transfer method, and what it does is it returns x, but transformed in a certain way. Here, the transformation is it's reduced it to 2 dimensions. So this is the data of the irises reduced to 2 dimensions. You can see that here it worked quite well because I can easily separate the setosa from the others. We can do this with more complicated models, but I will skip them in the interest of time. And now I want to illustrate how we can chain transformations. So we are going to be looking at chaining a Pca with a support vector machine. And we're going to do this on a data set of faces. So these are the faces, and we're going to try to recognize people in these faces. As a disclaimer, the state of the art to recognize people is not to use SVMs or even to use Scikit-Learn. Face recognition should be done using deep learning. It's the same underlying concepts than those that I'm talking about today, but with more complicated models. So what we're trying to do here, we're going to try to do a very simple model because we don't have a lot of data. And what we will do is that those faces are very high dimension. So we're going to use Pca to reduce the dimensionality. And then we are going to use a supervised learning model on top of this. So we're going to need to chain Pca and the supervised learning model. Okay, so the first thing we'll do is we'll split our data in train and test data. Then we will use the Pca to reduce the dimension. So we will fit the Pca on the train data. And I'm just going to skip this, and we can transform the data to obtain a reduced data. And we should transform the train, but also the test. Okay, so we fitted the Pca on the train, and then we need to transform the train and the test. So we have a reduced dimension. We only have 150 features now. And then we can use a supervised learning model. And here we're going to use a support vector machine. And we can fit it on the reduced data. And then we can predict. And here we are predicting. Okay? So, and we can measure the important thing is that we are predicting the reduced data because the SVM has been fitted on the reduced data, so we need to use the reduced data to predict. and we can measure the error and find that it works reasonably well. Now, something that is important is that I need to fit the PCA only on the train data. Because if the PCA sees the test data, then it will not give me a good evaluation. I will not be able to have a good evaluation of the prediction error. I will not be able to have a good evaluation of the error that I make when I have new data that comes in. So in what I showed you before, we needed to fit first the PCA, then the SVM, and each time we needed to be careful about which data we put in, only to put in the train data. In Scikit-Learn, there is the pipeline object that enables us to chain unsupervised transforms with a supervised step. So if I want to chain a PCA and an SVM, I can do this using the pipeline applied to, and the way I will build it is first I will give it a PCA, so a PCA model with the corresponding parameters, and then I will give it an SVM. And then the pipeline is an object. And like every single Scikit-Learn object, I can fit it on the data. So I can fit it on X train and Y train, and what it will do is that it will first fit the PCA on X train, and it will transform X train with the PCA, and then it will pass this to the SVM, and it will fit the SVM. So it's doing this chain of transformation for me. And so this is nice because then I can use it as any Scikit-Learn classifier. I could, for instance, put this in a cross-val score to measure its error. And so one thing that I could do, and I'm going to skip over to this part, is that I could chain everything together, and I could put this pipeline inside a grid search CV to tune all the parameters of the pipeline. And I believe that I have this at the end of this chapter. Okay, to find this, I will need to go to the example, the eigenface is example. And so if I go to the, I have the pipeline. Oh, no, I don't have it. Well, so I don't have this example. Well, I can show you how it will work. I have 5 minutes and I will show you how it will work, and I will have to type along. So I'm going to open the notebook. So I'm going to open the notebook in Jupyter. So here's the notebook. Is there a way to reduce dimension using class information? You can use an LDA to do this, but there's no, I would say there's no good way, no way that satisfies me. So I can run all the cells. So what this will do, if I run all the cells, is it will reproduce what I was showing you in the web page. It's just running them. And then what I will need to do is I will need to use, so it's running them, and then I will need to use grid search CV. So I'm importing grid search CV. And I will, so what I will do is that I will create a grid search CV. I'm going to call this grid. And so I will create a grid search CV. I will give it as a model my classifier. And then what I want to do, so my classifier is a pipeline. We can look at the classifier, and it's a pipeline with two steps, Pca and SVM. And what I want to do is I want to choose the number of components of the Pca. And so I will do this by defining a specific parameter grid. So the parameter grid of the grid search CV takes a dictionary where the names of the keys are the names of the parameters that I want to modify. And I want to modify the end component parameter of the Pca. And the way I write this with Scikit-Learn is I write Pca underscore end component. So it means I'm modifying the end components parameter of the Pca. And I'm going to try several values, 10, 50, 150, and 300. I hope this won't take too long to run. Okay, and I think this should be good. Okay. So now I can fit this to the data. Oh, I will add verbosity. I will increase the verbosity to see things better, and I will use parallel computing to go faster. Okay, I can fit this to the data, and what you can see is that it's doing many things in parallel. It's splitting the data. It's doing a cross-validation loop, and it's varying the number of components in the Pca. Oh, so it has already finished. And so then we can look at what the parameters it has chosen. And it has chosen the best parameter was 150. So it was the one that I already had before. Okay? And this was just a short introduction. We're out of time, but it was just a short introduction. However, I covered the most important things, the API of Scikit-Learn with the model, fit, transform, predict, cross-validation to measure prediction performance and to choose the best model or the best parameters, and grid search to do this in a clean way, and pipeline to chain several transformers. Thank you very much for listening, and thank you very much to Amanda for the translation.
Thank you. Thank you, Gaël. Thank you for this interesting and practical and interactive class. And I hope the participants have enjoyed as much as we did. As we have a very diverse audience, I think it will be interesting for people starting machine learning to know what they need to start using Scikit-Learn. Can you briefly explain it?
What they need to start
Yes,
using
to start using Scikit-Learn. Yeah.
Nothing.
Good.
They can use it online. There is binder instances. Let's see if it's, let's go to the, so something that I did not describe is the Scikit-Learn website. And it's important because we have a very a documentation that explains many things. And if you go to the examples, there are many examples, and you can take one example, and if you go to the bottom of the example, there is a button that says Launch Binder. And if I click on this, this will create a computer on the cloud on which you can play with the code. So you don't even need to install Scikit-Learn to use it.
Okay.
So nothing. And next step is data.
and data, very important. Yeah, great. And you mentioned that there are many methods that they have parameters. Is there any way for automatically deciding what is the best method for a given problem, or what is the correct setting for the parameters?
There is this notion of AutoML, which consists in basically using cross-validation in an aggressive way to set parameters. However, it is important to keep in mind that we usually say there's no free lunch. You don't get, if you try too many things, you will get things that seem to work by chance. So in the user guide, where is this? We used to have, oh, I don't remember what it is. We used to have a diagram of what to choose, what method to use depending on the data you have. I don't. Basically, I don't remember where it is. Basically, the idea being that you can usually focus on a small number of models to try. And these days, most people work on databases with heterogeneous data, that heterogeneous columnar data. And in those settings, I would say focus on the gradient boosting. They tend to work well in general. So what's the question I'm getting is, what's the problem to automate the selection of hyperparameter? Well, you have two problems. One is the computational cost. If you try everything, it will be very costly. Oh, thank you. The map, I don't know. So Javier shared the map I was looking for. So in terms of the limitation of AutoML, there are two limitations. One is the cost. It can be extremely costly. And in practice, what we do is that we reduce, so we experts, quote unquote experts, we reduce our model search to models that we think may work. And this is maybe a good way of, you know, reducing a bit your exploration. So we, you know, if we have a lot of data and the data is of columnar form, we will use a gradient boosting regressor, which is not on this figure because it's too recent. How sad. The other problem, which is related, is that if we try too many things, we will get overfit in AutoML. Okay, we will select models that seem to work well, but just because of chance. So I'm getting more questions. One is how to identify bias on a machine learning problem. That's an interesting question. Well, first you need to define clearly bias. There are different definitions of this term, but the typical definition that is used these days is that you have a feature that is related to your target, a feature of the data that is related to your target, but you don't want your prediction to relate to the target. One example is sex and salary. In existing databases, women tend to be paid less well than men, all things equal. So that is ideally not something that you would like to capture and reflect. So, well, there are different answers to your questions, how to identify bias on the machine learning problems. One of them that I like is to create a test set on which the data is not the feature that you're trying to predict is not correlated to the outcome. So if you can have a test set on which, for instance, sex is not related to income, then you can test whether a classifier has learned this bias or not. One reason I like this is because it's a paper we published. So I'm biased, but I think that's a good way of doing this. So you can craft such a data set by taking a smaller fraction of your data set where you have well-paid women and equally well-paid men. Are there any plans to include explanation of the models? So the answer is yes, in a sense. We are slowly working on this. And the next, so we have partial dependency plots. Where can I find this? So we have partial dependency plots. I should be able to find them here. Partial dependency. I think it's in Scikit-Learn plotting. Yes. So partial dependence plots are one way of inspecting model predictions. So you can see them here. One thing that we've learned with explainable AI and interpretable AI is that it's very important. The first thing we need to do is to get people to understand the models. And so for this, we've been working on the documentation and the examples. And there's a new section of the documentation that's called inspection, in which we discuss many things. And some of this is not about coding. We have this very long example that was done by Karen Marmo that really discusses how to interpret the coefficients of a linear model. And there is no new code. It's just explanations. So are there any more questions?
Yeah, I think not in the chat. I have last question for you. The search process for parameters is a very computational intense process. Can you point out what alternatives are there to do this in a way that is more efficient?
Sorry, I did not understand the question.
So the questions, I will read it again. The search process for parameters is a very computational intense process. Can you point out what alternatives are there to do this in a way that is more efficient?
Well, what
in terms of
one answer
computational?
to this?
Yep.
One answer to this is simply to have models that run faster. And so this is something we're working on. And this, the difference between the gradient boosting regressor and the HIST gradient boosting regressor is that the HIST version is much faster. It's not exactly equivalent, but it's much, much faster. So that's the first thing. We're trying to make models much faster. And another thing I really believe in is to reduce the search space. If we know that a small number of parameters, we need to test only a small number of parameters, and we need to vary them with only a small number of values, this goes much faster. So I believe that the combination of those two things is the most promising approach. There are sophisticated AutoML approaches, but we found that they can easily break, and so they're not integrated in Scikit-Learn. So I have a few other questions. One question is about self-organizing maps. No, they're not part of Scikit-Learn. This relates to a difficult choice that we need to make on a regular basis, which is what should be included in Scikit-Learn and what should not be. And it's always difficult to make those choices, but we're using a combination of popularity and practical usefulness. And by those standards, we've decided that self-organizing maps, we would not include them because we're not sure they bring something that's crucially useful given the modern tools. What is the vision for the next years of Scikit-Learn? Well, we want Scikit-Learn to be faster. We want Scikit-Learn to work better on heterogeneous data. So one thing we've been working a lot on is improving missing values support. We've been improving our gradient boosting support. We want better inspection. So we're working a lot on better inspection. I think that soon we will be able to support directly pandas data frame and to support feature names. So naming of the different features. So for instance, if I have a feature that is sex, I need to be able to interpret my model knowing that it's sex. We would like to be able to pass extra information, such as a protected attribute. So I want my classifier to be independent of sex. I want to predict the salary independent of sex. This is not something I can do in Scikit-Learn today. Hopefully, we will be able to do this soon. So do I think that machine learning will become a commodity? I do think that machine learning will become a commodity for the better or for the worse. For the better, because I believe that we get a better world by enabling more people because it levels the field. However, I also believe that people will make mistakes by not understanding the methods that they use, which is fine. It happens all the time. People make mistakes driving cars, but making it easier to use won't fix those mistakes. And I believe we need to keep teaching the intuitions behind the data and behind the statistics.
Yes, I think we don't have more questions. Thank you. Thank you, Gaël. Thank you again for being part. Have enjoyed it, and thank you for all the interesting questions that you have put in here in the chat. Yes, I think we have a lot to do for keeping teaching, for keeping democratizing the access to machine learning. Yeah, I'm sure. And the academy is a way, is a mechanism for doing so. It's in fact a new type of digital school. Inria had recently launched, and the fact is that it intends to meet the needs of the industrials and the entrepreneurial, but also the students and the society in general. Well, I take the chance also to let you invited to our next masterclass. I will share my screen. Could you please allow me? Okay, can you see my screen?
Yeah.
Okay, good. So I take the chance to let you invited to our next masterclass that will take place next Tuesday, September 22nd. It's the masterclass on Riot. The title is Microcontroller-Based IoT, a hands-on Riot. And it will be taught by Alexandre Abadi, which is also an Inria researcher. And I let you invited for this. It will be also very interested masterclass, very practical too. It is well known for you that to address nowadays Internet of Things requirements, all the objects must provide communication capabilities and needs to be able to perform more and more complex tasks in parallel. So I let you invited because it will be a good way to get an introduction of the Riot operating system and the ecosystem around Riot and the possibilities for securing objects, and also for around the ecosystem of Riot, and also for the features by the system, and an overview of the IoT development. Okay, so thank you very much again, Gaël, for your participation, and thank you the participants that have joined us today. See you, all of you, next week. Bye-bye.
Thank you. Goodbye.
Goodbye.